There is an experiment so strange that the people who discovered it spent the rest of their lives arguing about what it means. Here's the setup. Fire single particles, one at a time, at a screen with two slits. Common sense says each particle goes through one slit or the other. But that is not what happens. Each particle somehow goes through both slits at once, interfering with itself, building up a striped pattern that only makes sense if each particle was a wave passing through both openings. Until you try to watch which slit it actually uses. The instant you look, it picks one. The pattern collapses. The universe behaves differently depending on whether it is being observed. This is the measurement problem. And a century later, we still don't know why it happens. To understand the problem, you need one idea: superposition. In quantum mechanics, before you measure it, a particle is not in one definite state. It's in a combination of all possible states at once. This is described by the wave function. An electron can be spin up and spin down simultaneously. A photon can be in two places at the same time. And here's the crucial part. This is not a lack of knowledge about which state it's really in. It's not that the particle has secretly chosen, and we just don't know yet. The mathematics says it is genuinely in all of those states at once. Until something forces a choice. Now here's where it gets sharp. The wave function evolves smoothly, predictably. It follows the Schrödinger equation. And that equation is completely deterministic. Give me the wave function now, and I can calculate it for any moment in the future. Exactly. No randomness. No surprises. But then comes the rupture. When you measure the system, the smooth wave function suddenly, discontinuously collapses to a single, definite value. And which value you get is random. Pure probability. There's a rule, the Born rule, that tells you the odds of each outcome. But nothing tells you why you got this particular result and not another. So quantum mechanics contains two completely different rules. Rule 1, smooth, deterministic evolution when nobody's looking. Rule 2, random, instantaneous collapse, the moment you measure. And nobody can explain how, or when, the switch between them happens. That's the measurement problem. So what counts as a measurement? This is the heart of it. Does measurement require a conscious observer? A human? Or just a lab instrument? Does a single atom bumping into the system count? When exactly does collapse happen? To show how absurd this gets, Erwin Schrödinger invented a thought experiment. You've heard of it. A cat in a sealed box. Inside, a vial of poison, rigged to break if a single radioactive atom decays. The decay is a quantum event. Random. Governed by the wave function. So until you open the box, the atom is in superposition. Decayed, and not decayed. At the same time. And if the atom is in superposition, then so is the poison. And so is the cat. The cat is alive and dead simultaneously. Schrödinger meant this as a joke. A reductio ad absurdum. Look how ridiculous quantum mechanics becomes if you take it literally. But here's the punchline. The universe didn't get the memo. In carefully controlled experiments, superposition is real. We've put molecules with thousands of atoms into two states at once. The cat is not just a metaphor. So what is actually going on? This is where physicists genuinely disagree. There are several serious interpretations. Let me give you 4. 1. The Copenhagen interpretation. Collapse is real and fundamental. The moment you measure, the wave function genuinely collapses. And asking what's really happening before measurement? Meaningless. Don't ask. For decades, this was the default. Shut up and calculate. 2. The many worlds interpretation. There is no collapse. Ever. Instead, every possible outcome actually happens each in its own branching universe. The cat is alive in one world, dead in another. And when you open the box, you split too. One version of you sees a live cat. Another version, in a parallel branch, sees a dead one. There are, right now, countless versions of you. 3. Decoherence. The superposition doesn't vanish, it leaks. The quantum system gets hopelessly entangled with its environment, air molecules, photons, the detector itself. This makes the superposition impossible to observe. It explains why we never see cats that are both alive and dead. But it explains the appearance of collapse, not why we get one specific outcome. 4. Pilot wave theory. Particles always have definite positions. There's no fuzziness. They're just guided by a hidden wave we can't directly see. Here's the maddening part. All 4 interpretations make exactly the same experimental predictions. Every single one. Which means we cannot run an experiment to find out which is true. Now you might be thinking, okay, this is just philosophy. Does it matter? It matters enormously. Quantum mechanics is the most successful theory in the history of science. It predicts experimental results to 12 decimal places. More precisely than anything else humans have ever measured. And yet, at its foundation, we do not understand what it's telling us about reality. That's not a small gap. That's a hole at the very center of our best theory. But here's where it stops being abstract. Quantum computers. They work by keeping qubits in superposition, doing many calculations at once in ways no classical computer can match. And their single greatest enemy? Decoherence. The exact same effect at the heart of the measurement problem. Every quantum computer on Earth is fighting a constant battle against its qubits collapsing too soon. Understanding measurement isn't a philosopher's hobby. It's the engineering problem that decides whether quantum computers work at all. The deepest mystery in physics is now also an industrial problem worth billions of dollars. The measurement problem leaves us with something humbling. Our best theory of reality works flawlessly. And we still don't know what it means. Maybe reality is fundamentally observer-dependent. Maybe there are infinite parallel versions of you, splitting every second. Maybe the question itself is somehow wrong. 100 years in, the argument continues. Next up, quantum entanglement. Einstein called it spooky action at a distance. He thought it proved quantum mechanics was incomplete, that something had to be missing. He was wrong. And the way we finally proved he was wrong won the Nobel Prize in 2022. Subscribe so you don't miss that one. And tell me in the comments, which interpretation do you believe? Copenhagen? Many worlds? Something else? I really want to know.